The Internals of Postgres for database administrators and system developers. Introduction. In this document, the internals of Postgres for database admins and system developers are described. Postgres is an open-source multi-purpose relational database which is widely used throughout the world. It is one huge system and the integrated subsystems, each of which has a particular complex feature and works with each other cooperatively. Although understanding the internal mechanism is crucial for both administration and integration using Postgres, its hugeness and complexity prevent it. The main purpose of this document is to explain how each subsystem works and to provide the whole picture of Postgres. This document is based on the second part of the book I wrote in Japanese in 2012, which is composed of 7 parts and covers version 11 and earlier. Contents. Chapter 1, Database Cluster, Databases and Tables. Chapter 2, Process and Memory Architecture. Chapter 3, Query Processing. Chapter 4, Foreign Data Wrappers. Chapter 5, Concurrency Control. Chapter 6, Vacuum Processing. Chapter 7, Heap-Only Tuple, HOT, and Index-Only Scans. Chapter 8, Buffer Manager. Chapter 9, Write-Ahead Logging, WAL. Chapter 10, Base Backup and Point-in-Time Recovery, PITR. Chapter 11, Streaming Replication. And here is a guide map. Chapter 1, Database Cluster, Databases, and Tables. This chapter and the next chapter summarize the basic knowledge of Postgres to help read the subsequent chapters. In this chapter, the following topics are described: the logical structure of a database cluster, the physical structure of a database cluster, the internal layout of a heap table file, the methods of writing and reading data to a table. If you are familiar with them, you may skip over this chapter. 1.1 Logical structure of a database cluster. A database cluster is a collection of databases managed by a Postgres server. If you hear this definition now for the first time, you might be wondering about it. But the term database cluster in Postgres does not mean a group of database servers. A Postgres server runs on a single host and manages a single database cluster. Figure 1.1 shows the logical structure of a database cluster. A database is a collection of database objects. In the relational database theory, a database object is a data structure used either to store or to reference data. A heap table is a typical example of it, and there are many more like an index, a sequence, a view, a function, and so on. In Postgres, databases themselves are also database objects and are logically separated from each other. All other database objects, e.g. tables, indexes, etc., belong to their respective databases. All database objects in Postgres are internally managed by respective object identifiers, OIDs, which are unsigned 4-byte integers. The relations between database objects and their respective OIDs are stored in appropriate system catalogs, depending on the type of objects. For example, OIDs of databases and heap tables are stored in PG_database and PG_class, respectively. So you can find out the OIDs you want to know by issuing the queries such as the following. Select datname OID from PG database where datname equals sampledb. Select relname OID from PG class where relname is sample table. 1.2 Physical structure of database cluster. A database cluster basically is one directory referred to as base directory. A database cluster is basically one directory referred to as base directory, and it contains some subdirectories and lots of files. If you execute the initdb utility to initialize a new database cluster, a base directory will be created under the specified directory. Though it is not compulsory, the path of the base directory is usually set to the environment variable pgdata. Figure 1.2 shows an example of a database cluster in Postgres. A database is a subdirectory under the base subdirectory, and each of the tables and indexes is at least one file stored under the subdirectory of the database to which it belongs. Although there are several subdirectories containing particular data and configuration files, there are several subdirectories containing particular data and configuration files. While Postgres supports table spaces, the meaning of the term is different from other relational database management systems. A table space in Postgres is one directory that contains some data outside of the base directory. Figure 1.2, an example of a database cluster. Files of tables, indexes, free space maps, and visibility maps. Base. Global, PG logical, PG stat, PG tablespace, etc. In the following subsections, the layout of a database cluster, databases, files associated with tables and indexes, and the tablespace in Postgres are described. 1.2.1 Layout of a database cluster. The layout of database cluster has been described in the official document. Main files and subdirectories in a part of the document have been listed in Table 1.1. Layout of files and subdirectories under the base directory. Files description. PG version, a file containing the major version number of Postgres. pghba.conf, a file to control Postgres client authentication. pgident.conf, a file to control Postgres username mapping. PostgreSQL.conf, a file to set configuration parameters. PostgreSQL.auto.conf, a file used for storing configuration parameters that are set in alter system, version 9.4 or later. Postmaster.ops, a file recording the command line options the server was last started with. Subdirectories description. Base, subdirectory containing per database subdirectories. Global, subdirectory containing cluster-wide tables such as PG database and PG control. PG commit TS, subdirectory containing transaction commit timestamp data, version 9.5 or later. PG clog, version 9.6 or earlier. Subdirectory containing transaction commit state data. It is renamed PG exact in version 10. Clog will be described in section 5.4. PG dynmem, subdirectory containing files used by the dynamic shared memory subsystem, version 9.4 later. PG logical, subdirectory containing status data for logical decoding, version 9.4 later. PG multi-exact, subdirectory containing multi-transaction status data, used for shared road logs. PG notify, subdirectory containing listen/notify status data. PG rep slot, subdirectory containing replication slot data, version 9.4 later. PG serial, subdirectory containing information about committed serializable transactions, version 9.1 or later. PG snapshots, subdirectory containing exported snapshots, 9.2 or later. The Postgres function PG export snapshot creates a snapshot information file in this subdirectory. PG stat, subdirectory containing permanent files for the statistics subsystem. PG stat temp, subdirectory containing temporary files for the statistics subsystem. PG subtrans, subdirectory containing subtransaction status data. PG tablespace, subdirectory containing symbolic links to tablespaces. PG two-phase, subdirectory containing state files for prepared transactions. PG wall, version 10 or later, subdirectory containing wall, write ahead logging segment files. It is renamed from PG xlog in version 10. PG exact, version 10 or later, subdirectory containing transaction commit state data. It is renamed from PG clog in version 10. PG xlog, version 9.6 or earlier, subdirectory containing wall segment files. It is renamed to PG wall in version 10. 1.2.2 Layout of databases. A database is a subdirectory under the base subdirectory, and the database directory names are identical to the respective OIDs. For example, when the OID of the database sampledb is 16,384, its subdirectory name is 16,384. 1.2.3 Layout of files associated with tables and indexes. Each table or index whose size is less than 1 gigabyte is a single file stored under the database directory it belongs to. Tables and indexes as database objects are internally managed by individual OIDs, while those data files are managed by the variable rel file node. The rel file node values of tables and indexes basically, but not always, match the respective OIDs. The details are described below. Let's show the OID and rel file node of the table sample table. Select rel name, OID, rel file node from PG class, where rel name is sample table. From the result above, you can see that both OID and rel file node values are equal. You can also see that the data file path of the table sample table is base / 16,384 / 18,740. The rel file node values of tables and indexes are changed by issuing some commands, e.g. truncate, reindex, cluster. For example, if we truncate the table sample table, Postgres assigns a new file node, 18,800 18,712 to the table, removes the old data file, 18,740, and creates the new one, 18,812. Truncate sample table, and then run the same query. Now we have a new rel file node. In version 9.0 or later, the built-in function pgRelationFilePath is useful, as this function returns the file path name of the relation with the specified OID or name. Select pgRelationFilePath sample table. When the file size of tables and indexes exceeds 1 gigabyte, Postgres creates a new file named like relfilenode.1 and uses it. If the new file has been filled up, the next new file named like relfilenode2 will be created, and so on. The maximum file size of tables and indexes can be changed using the configuration option with seg size when building Postgres. Looking carefully at the database subdirectories, you will find out that each table has two associated files suffixed respectively with FSM and VM. Those are referred to as free space map and visibility map, storing the information of the free space capacity and the visibility of each page within the table file, respectively. Indexes only have individual free space maps and don't have visibility map. A specific example is shown below. Free space map, visibility map. They may also be internally referred to as the forks of each relation. The free space map is the first fork of the table index data file. The fork number is 1. The visibility map, the second fork of the table's data file, the fork number is 2. The fork number of the data file is 0. (1.2.4) Table spaces. A table space in Postgres is an additional data area outside the base directory. This function has been implemented in version 8.0. Figure 1.3 shows the internal layout of a table space and the relationship with the main data area. Table space. A table space is created under the directory specified when you issue create tablespace statement, and under that directory, the version specific subdirectory, e.g. pg 9.4 2014 09 29.1 will be created. The naming method for version specific one is shown below. PG major version, catalog version number. For example, if you create a tablespace, new tablespace at home Postgres tablespace, whose OID is 16,386, a subdirectory such as PG 9.4 2014 09 29.1 would be created under the tablespace. The tablespace directory is addressed by a symbolic link from the PG tablespace subdirectory, and the link name is the same as the OID value of the tablespace. If you create a new database, OID 16,387 under the table space, its directory is created under the version-specific subdirectory. If you create a new table which belongs to the database created under the base directory, first, the new directory, whose name is the same as the existing database OID, is created under the version-specific subdirectory, and then the new table file is placed under the created subdirectory, or the created directory. Create table, new table, table space, new table space. And then select PG relation file path, new table. (1.3) Internal layout of a heap table file. Inside the data file, heap table and index, as well as the free space map and visibility map, it is divided into pages, or blocks, of a fixed length. The default is 8,192 byte, or 8 kilobits. Those pages within each file are numbered sequentially from 0, and such numbers are called as block numbers. If the file has been filled up, Postgres adds a new empty page at the end of the file to increase the file size. Internal layout of pages depends on the data file types. In this section, the table layout is described as the information will be required in the following chapters. Block number, table file, and a page, 8 kilobit size page. And inside each page, we have a whole bunch of these things. Header information, line pointers, tuples, heap tuples, record data. And we have free space, hole. A page within a table contains 3 kinds of data described as follows. Heap tuples. A heap tuple is a record data itself. They are stacked in order from the bottom of the page. The internal structure of tuple is described in 5.2 in chapter 9 as the knowledge of both concurrency control and wall in Postgres are required. Line pointers. A line pointer is 4 bytes long and holds a pointer to each tuple, heap tuple. It is also called an item pointer. Line pointers form a simple array which plays the role of index to the tuples. Each index is numbered sequentially from 1 and called offset number. When a new tuple is added to the page, a new line pointer is also pushed onto the array to point to the new one. Header data. Header data defined by the structure page header data is allocated in the beginning of the page. It is 24 bytes long and contains general information about the page. The major variables of the structure are described below. PD LSN. This variable stores the LSN of xlog record written by the last change of this page. It is an 8-byte unsigned integer related to the write-ahead logging mechanism. PD checksum. This variable stores the checksum value of this page. Note that this variable is supported in version 9.3 or later. In earlier versions, this part had stored the timeline ID of the page. PD lower, PD upper. PD lower points to the end of the line pointers, and PD upper to the beginning of the newest heap tuple. PD special. This variable is for indexes. In the page within tables, it points to the end of the page. In the page within indexes, it points to the beginning of special space, which is the data area held only by indexes and contains the particular data according to the kind of index types, such as btree, gist, gin, etc. An empty space between the end of line pointers and beginning of the newest tuple is referred to as free space or hole. To identify a tuple within the table, tuple identifier TID is internally used. A TID comprises a pair of values, the block number of the page that contains the tuple and the offset number of the line pointer that points to the tuple. A typical example of its usage is index. The structure of page header data is defined in source include storage buff page. In addition, heap tuple whose size is greater than 2 kilobytes, about 1/4 of 8 kilobytes, is stored and managed using a method called toast, the oversized attribute storage technique. 1.4 Methods of writing and reading tuples. In the end of this chapter, the methods of writing and reading heap tuples are described. 1.4.1 Writing heap tuples. Suppose a table composed of one page which contains just one heap tuple. The PD lower of this page points to the first line pointer, and both the line pointer and the PD upper point to the first heap tuple. See figure 1.5a. When the second tuple is inserted, it is placed after the first one. The second line pointer is pushed onto the first one, and it points to the second tuple. The PD lower changes to point to the second line pointer, and the PD upper to the second heap tuple. See figure 1.5b. Other header data within this page, e.g. PD LSN, PG checksum, PG flag, are also rewritten to appropriate values. 1.4.2 Reading heap tuples. Two typical access methods, sequential scan and btree index scanned, are outlined here. Sequential scan. All tuples in all pages are sequentially read by scanning all line pointers in each page. btree index scan. An index file contains index tuples, each of which is composed of an index key and a TID pointing to the target heap tuple. If the index tuple with the key that you are looking for has been found, Postgres reads the desired heap tuple by using the obtained TID value. The description of the way to find the index tuples in btree index is not explained here, as it is very common and the space here is limited. See the relevant materials. For example, in figure 1.6b, the TID value of the obtained index tuple is block equals 7, offset equals 2. It means that the target heap tuple is the second tuple in the 7th page within the table. So Postgres can read the desired heap tuple without unnecessarily scanning in the pages. Index. Postgres also supports TID scan, bitmap scan, and index-only scan. TID scan is a method that accesses a tuple directly by using the TID of the desired tuple. For example, to find the first tuple in the 0th page within the table, issue the following query. Select ctid data from sample data where ctid equals 0, 1. Chapter 2. Process and Memory Architecture. In this chapter, the process architecture and memory architecture in Postgres are summarized to help to read the subsequent chapters. If you are already familiar with them, you may skip over this chapter. 2.1. Process Architecture. Postgres is a client-server type relational database management system with a multi-process architecture and runs on a single host. A collection of multiple processes cooperatively managing one database cluster is usually referred to as a Postgres server, and it contains the following types of processes. A Postgres server process is a parent of all processes related to a database cluster management. Each backend process handles all queries and statements issued by a connected client. Various background processes perform processes for each feature, e.g., vacuum and checkpoint processes for database management. In the replication-associated processes, they perform the streaming replication. In the background worker process, supported from version 9.3, it can perform any processing implemented by users. In the following subsections, the details of the first three types of processes are described. So figure 2.1, an example of the process architecture in Postgres. We have a client, and we have this Postgres server process, a couple forks, shared memory, database cluster, a whole bunch of subprocesses. This figure shows processes of a Postgres server, a Postgres server process, 2 backend processes, 7 background processes, and 2 client processes. The database cluster, the shared memory, and the 2 client processes are also illustrated. 2.1.1 Postgres server process. As already described above, a Postgres server process is a parent of all in a Postgres server. In earlier versions, it was called Postmaster. By executing the pgctl util with start option, a Postgres server process starts up. Then, it allocates a shared memory area in memory, starts various background processes, starts replication-associated processes and background worker processes if necessary, and waits for connection requests from clients. Whenever receiving a connection request from a client, it starts a backend process, and then the started backend process handles all queries issued by the connected client. A Postgres server process listens to one network port. The default port is 5432. Although more than one Postgres server can run on the same host, each server should be set to listen to a different port number in each, e.g. 5432, 5433, etc. (2.1.2) Backend processes. A backend process, which is also called Postgres, is started by the Postgres server process and handles all queries issued by one connected client. It communicates with the client by a single TCP connection and terminates when the client gets disconnected. As it is allowed to operate only one database, you have to specify a database you want to use explicitly when connecting to a Postgres server. Postgres allows multiple clients to connect simultaneously, The configuration parameter max connections controls the maximum number of clients. The default is 100. If many clients, such as web applications, frequently repeat the connection and disconnection with a Postgres server, it increases both costs of establishing connections and of creating backend processes, because Postgres has not implemented a native connection pooling feature. Such circumstance has a negative effect on performance of the database server. To deal with such a case, a pooling middleware, either PG Bouncer or PG Pool 2, is usually used. 2.1.3 Background Processes. Table 2.1 shows a list of background processes. In contrast to the Postgres server and the backend process, it is impossible to explain each of the functions simply, because these functions depend on the individual specific features and Postgres internals. Thus, in this chapter, only introductions are made. Details will be described in the following chapters. Background processes. Process description. Background writer. In this process, dirty pages of the shared buffer pool are written to a persistent store, e.g. HDD, SSD, on a regular basis gradually. In version 9.1 or earlier, it was also responsible for checkpoint process. Checkpointer. In this process, in version 9.2 or later, checkpoint process is performed. Auto vacuum launcher. The auto vacuum worker processes are invoked for vacuum process periodically. More precisely, a request to create the auto vacuum workers to the Postgres server. Wall writer. This process writes and flushes periodically the wall data on the wall buffer to persistent storage. Statistics collector. In this process, statistics information such as for pgstat activity and for pgstat database, etc. is collected. Logging collector, logger. This process writes error messages into log files. Archiver. In this process, archiving logging is executed. The actual processes of a Postgres server is shown here. In the following example, one Postgres server process, PID 9687, two backend processes, PIDs 9697 and 9717, and several background processes listed in Table 2.1 are running. Logger process, checkpointer, writer, wall writer, auto vacuum, archiver, and this is neat. 2.2 Memory architecture. Memory architecture in Postgres can be classified into two broad categories. Local memory area, allocated by each backend process for its own use. Shared memory area, used by processes for a Postgres server. In the following subsections, those are briefly described. Figure 2.2, Memory architecture of Postgres. So I have backend process, which has temp buffers, workmem, and maintenance workmem. Then shared memory, which has a shared buffer pool, a wall buffer, and commit log, clog. And then the database cluster. 2.2.1 Local memory area. Each backend process allocates a local memory area for query processing. Each area is divided into several sub-areas, whose sizes are either fixed or variable. Table 2.2 shows a list of the major subareas. The details will be described in the following chapters. So 2.2, local memory area, subarea description. Work mem. Executor uses this area for sorting tuples by, order by, and distinct operations, and for joining tables by merge join and hash join operations. Maintenance work mem. Some kinds of maintenance operations, e.g. vacuum, reindex, use this area. Temp buffers. Executor uses this area for storing temporary tables. 2.2.2 Shared memory area. A shared memory area is allocated by a Postgres server when it starts up. This area is also divided into several fixed-sized subareas. Table 2.3 shows a list of the major subareas. So shared memory area, subarea description. Shared buffer pool. Postgres loads pages within tables and indexes from a persistent storage to here and operates them directly. Wall buffer. To ensure that no data has been lost by server failures, Postgres supports the wall mechanism. Wall data, also referred to as xlog records, are transaction logs in Postgres. And wall buffer is a buffering area for the wall data before writing to a persistent storage. Commit log. Commit log, or clog, keeps the states of all transactions, e.g. in progress, committed, aborted, for concurrency control, CC mechanism. In addition to them, Postgres allocates several areas as shown below. Subareas for the various access control mechanisms, e.g. semaphores, lightweight locks, shared and exclusive locks, etc. Subareas for the various background processes, such as checkpointer and auto vacuum. Subareas for transaction processing, such as save point and two-phase commit, and others. Chapter 3. Query processing. As described in the official document, Postgres supports a very large number of features required by the SQL standard of 2011. Query processing is the most complicated subsystem in Postgres, and it efficiently processes the supported SQL. This chapter outlines this query processing. In particular, it focuses on query optimization. This chapter comprises the following three parts. Part 1. This section overviews the query processing in Postgres. Part 2. This part explains the steps followed to obtain the optimal plan of a single table query. The processes of estimating the cost and creating the plan tree are explained. The operation of the executor is briefly described. Part 3. This part explains the process of obtaining the optimal plan of a multiple table query. 3 join methods are described: nested loop, merge, and hash join. The process of creating the plan tree of a multiple table query is explained. Postgres supports 3 technically interesting and practical features, namely foreign data wrappers, FDW, parallel query, and JIT compilation, which is supported from version 11. The first 2 of them will be described in Chapter 4. The JIT compilation is out of the scope of this document, and see the official document for details. 3.1 Overview. In Postgres, although the parallel query implemented in version 9.6 uses multiple background processes, a background worker processes, a backend process basically handles all queries issued by the connected client. This backend consists of 5 subsystems as shown below: parser, analyzer, rewriter, planner, executor. Parser. The parser generates a parse tree from a SQL statement in plain text. Analyzer. The analyzer carries out a semantic analysis of a parse tree and generates a query tree. Rewriter. The rewriter transforms a query tree using the rules stored in the rule system if such rules exist. Planner. The planner generates the plan tree that can most effectively be executed from the query tree. Executor. The executor executes the query via accessing the tables and indexes in the order that was created by the plan tree. In this section, an overview of these subsystems is provided. Due to the fact that the planner and the executor are very complicated, a detailed explanation of these functions will be provided in the following sections. 3.1.1 Parser. The parser generates a parse tree that can be read by subsequent subsystems from a SQL statement in plain text. Here a specific example is shown in the following without a detailed description. Let us consider the query shown below. Select ID data from table A where ID is less than 300. Order by data. A parse tree is a tree whose root node is the select statement structure defined in parsenodes.h. Figure 3.2b illustrates the parse tree of the query shown. Select statement, list, node, list target, res target, column ref, table A, fields ID, table, range var, the from clause, node, where clause, ID, sort by. The elements of the select query and the corresponding elements of the parse tree are numbered the same. For example, 1 is an item of the first target list, and it is the column ID of the table. 4 is a where clause, and so on. Due to the fact that the parser only checks the syntax of an input when generating a parse tree, it only returns an error if there is a syntax error in the query. The parser does not check the semantics of an input query. For example, even if the query contains a table name that does not exist, the parser does not return an error. Semantic checks are done by the analyzer. 3.1.2 Analyzer. The analyzer runs a semantic analysis of a parse tree generated by the parse tree and generates a query tree. The root of a query tree is the query structure, defined in parsenodes.h. This structure contains metadata of its corresponding query, such as the type of this command, select, insert, or others, and several leaves. Each leaf forms a list or a tree and holds data of the individual particular clause. Example of a query tree. So a target entry, range table entry, target list, R table, join tree, sort clause. Subquery, null. The above query tree is briefly described as follows. The target list is a list of columns that are the result of this query. In this example, this list is composed of 2 columns, ID and data. If the input query tree uses star, asterisk, the analyzer will explicitly replace it in all of the columns, replace it with all of the columns. The range table is a list of relations that are used in this query. In this example, this table holds the information of the table A, such as the OID of this table and the name of this table. The join tree stores the from clause and the where clauses. The sort clause is a list of sort group clause. 3.1.3 Rewriter. The rewriter is the system that realizes the rule system and transforms a query tree according to the rules stored in PG rules in the PG rules system catalog if necessary. The rule system is an interesting system in itself. However, the descriptions of the rule system and the rewriter have been omitted to prevent this chapter from becoming too long. View. Views in Postgres are implemented by using the rule system. When a view is defined by the createView command, the corresponding rule is automatically generated and stored in the catalog. Assume the following view is already defined and the corresponding rule is stored in the PG rules system catalog. Create view employees list as select e.id, e.name, and d.name as department. From employees as E, departments as D, where e.department.id or department ID equals d.id. When a query that contains a view shown below is issued, the parser creates the parse tree as shown in figure 3.4a. So select star from employees list. At this stage, the rewriter processes the range table node to parse a tree of the subquery, which is the corresponding view stored in PG rules. Example of the rewriter stage. This. Subquery. Since Postgres realizes views using such a mechanism, views could not be updated until version 9.2. However, views can be updated from version 9.3 onwards. Nonetheless, there are many limitations in updating the view. 3.1.4 Planner and Executor. The planner receives a query tree from the rewriter and generates a query plan tree that can be processed by the executor most effectively. The planner in Postgres is based on pure cost-based optimization. It does not support rule-based optimization and hints. This planner is the most complex subsystem in relational database management system. Therefore, an overview of the planner will be provided in the subsequent sections of this chapter. PG hint plan. Postgres does not support the planner hints in SQL, and it will not be supported forever. If you want to use hints in your queries, the extension referred to PG hint plan will be worth considering. As in other RDBMS, the explain command in Postgres displays the plan tree itself. A specific example is shown below. Explain, select star from table A, where ID is less than 300, order by data. Here's the query plan. Sequential scan, filter, 4 rows. This result shows the plan tree shown in figure 3.5. Plan statement, sort node, sequential scan. A plan tree is composed of elements called plan nodes, and it is connected to the plan tree list of the planned statement structure. These elements are defined in plannodes.h. Details will be explained in section 3.3.3. Each plan node has information that the executor requires for processing, and the executor processes from the end of the plan tree to the root in the case of a single table query. For example, the plan tree shown in figure 3.5 is a list of a sort node and a sequential scan node. Thus, the executor scans the table A, by a sequential scan and then sorts the obtained result. The executor reads and writes tables and indexes in the database cluster via the buffer manager described in Chapter 8. When processing a query, the executor uses some memory areas, such as temp buffers and workmem, allocated in advance, and creates temporary files if necessary. In addition, when accessing tuples, Postgres uses the concurrency control mechanism to maintain consistency and isolation of the running transactions. The concurrency control mechanism is described in Chapter 5. Figure 3.6, the relationship among the executor, buffer manager, and temporary files. So we have temporary files, buffer manager, we have a backend process, an executor, some workmem. 3.2 Cost estimation in single table query. Postgres' query optimization is based on cost. Costs are dimensionless values, and these are not absolute performance indicators, but are indicators to compare the relative performance of operations. Costs are estimated by the functions defined in cost size C. All of operations executed by the executor have the corresponding cost functions. For example, the costs of sequential scans and index scans are estimated by cost sequential scan and cost index, respectively. In Postgres, there are three kinds of costs: startup, run, and total. The total cost is the sum of startup and run costs. Thus, only the startup and run costs are independently estimated. The startup cost is the cost expended before the first tuple is fetched. For example, the startup cost of the index scan node is the cost to read index pages to access the first tuple in the target table. The run cost is the cost to fetch all tuples, and the total cost is the sum of those. The explain command shows both startup and total costs in each operation. The simplest example is shown below. Explain select star from table. In line 4, the command shows information about the sequential scan. In the cost section, there are two values, 0 and 145. In this case, the startup and total costs are 0 and 145 respectively. In this section, we will explore how to estimate the sequential scan, index scan, and sort operation in detail. In the following explanations, we use a specific table and an index that are shown below. So create table, int ID, primary key, data int, create index, table data index on table data, insert into table, select generate series 1 to 10,000, and then for ID, and then generate series 1 to 10,000 for data, then analyze and describe table. 3.1.2 Sequential scan. The cost of a sequential scan is estimated by cost sequential scan function. In this subsection, we'll explore how to estimate sequential scan cost of the following query. Select star from table where ID is less than 8,000. In the sequential scan, the startup cost is equal to 0. and the run cost is defined by the following equation. Run cost equals CPU run cost plus disk run cost, and that means the CPU tuple cost plus CPU operator cost times number of tuples plus sequential page cost times number of page, where sequential page cost, CPU tuple cost, and CPU operator cost are set in the PostgreSQL.conf file, and the default values are 1.0, 0.01, and 0.0025 respectively. N tuple and N page are the numbers of all tuples and all pages of this table respectively, and these numbers can be shown using the following query. Select rel pages, rel tuples from PG class, where rel name equals table. Thus, run cost equals 0.01 plus 0.0025 times 10,000 plus 1.0 times 45 equals 170. Finally, the total cost is the start cost, which is 0, plus 170, so it's 170. For confirmation, the result of the explain query, the explain command of the above query is shown below. In line 4, we can find that the startup and total costs are 0 and 170 respectively, and it is estimated that 8,000 rows, tuples, will be selected by scanning all rows. In line 5, a filter ID less than 1,000 of the sequential scan is shown. More precisely, it is called a table level filter predicate. Note that this type of filter is used when reading all the tuples in the table, and it does not narrow the scanned range of the table pages. As understood from the run cost estimation, Postgres assumes that all pages will be read from storages. That is, Postgres does not consider whether the scanned page is in the shared buffers or not. 3.2.2 Index Scan. Although Postgres supports some index methods, such as btree, gist, gin, and brin, the cost of the index scan is estimated using the common cost function costIndex. In this subsection, we explore how to estimate the index scan cost of the following query. Select ID table from table where data is less than 240. By estimating the cost, the numbers of the index pages and the index tuples, number of index page and number of index tuple, are shown below. Select rel pages, rel tuples from PG class where rel name equals table data index. So rel pages 30 and rel tuples 10,000. 3.2.2.1 Startup cost. The startup cost of the index scan is the cost to read the index pages to access the first tuple in the target table, and it is defined by the following equation. Startup cost. Take the ceiling of log base 2 of number of tuples in the index plus the h index plus 1 and all of that, and then plus the h index plus 1 times 50 times the CPU operator cost, where h index is the height of the index tree. In this case, according to 3, the n of index tuple, the number of tuples in the index is 10,000. The height of the index tree is 1. The CPU operator cost is 0.0025 by default. Thus, the startup cost is the ceiling of log base 2 of 10,000 plus 1 plus 1 times 50, and all of that times 0.0025, with the result being 0.285. Run cost. The run cost of the index scan is the sum of the CPU costs and the I/O, input-output costs of both the table and the index. Run cost equals index CPU cost plus table CPU cost plus index I/O cost plus table I/O cost. If the index only scans, which are described in section 7.2, can be applied, table CPU cost and table I/O cost are not estimated. The first three costs, i.e. index CPU cost, table CPU cost, and index I/O cost, are shown below. Index CPU cost. Selectivity times number of tuples in the index times the sum of CPU index tuple cost plus qual op cost. Table CPU cost equals selectivity times number of tuples times CPU tuple cost. And index I/O cost equals the ceiling of selectivity times number of pages in the index times random page cost, where CPU index tuple cost and random page cost are set in the PostgreSQL.conf file. The defaults are 0.005 and 4.0 respectively. Qual op cost is, roughly speaking, the evaluating cost of the index, and is shown without much explanation here. Qual op cost equals 0.0025. Selectivity is the proportion of the search range of the index by the specified where clause. It is a floating point number from 0 to 1, and is described in detail below. For example, selectivity times number of tuples means the number of the table tuples to be read. Selectivity times number of pages in the index means the number of index pages to be read, and so on. Selectivity. The selectivity of query predicates is estimated using histogram bounds, or the MCV, most common value, both of which are stored in the statistics information, PG stats. Here, the calculation of the selectivity is briefly described using specific examples. More details are provided in the official document. The most common value of each column of a table is stored in the PG stats view as a pair of columns of most common vals and most common freaks. Most common vals is a list of the most common values in the column. Most common freaks is a list of the frequencies of the MCVs. A simple example is shown as follows. The table countries has two columns. A column country that stores the column name, and a column continent that stores the continent name to which the country belongs. So we have let's describe the countries table. We have a country and a continent with an index on continent. And then select continent, count star as number of countries, and count star divided by the select count star from countries as number of countries divided by all countries. From countries, group by continent, order by number of countries, descending. Let us consider the following query, which has a where clause, continent equals Asia. Select star from countries where continent equals Asia. In this case, the planner estimates the index cost. In this case, the planner estimates the index scan cost using the most common value of the continent column. The most common vowels and most common frequencies of this column are shown below. /x, expanded displays on. Select most common vowels and most common frequencies from PG stats, where table name is countries and at name is continent. The value of the most common frequencies corresponds to Asia. Of the most common vowels, it is 0.227979. Therefore, 0.227979 is used as the selectivity in this estimate. If the most common value cannot be used, the value of the histogram bounds of the target column is used to estimate the cost. Histogram bounds is a list of values that divide the column's values into groups of approximately equal population. A specific example is shown. In this value, this is the value of histogram bounds of the column data in the table. Select histogram bounds from PG stats, where table name equals table and at name equals data. Histogram bounds. By default, the histogram bounds is divided into 100 buckets. Figure 3.7 illustrates the buckets and the corresponding histogram bounds in this example. Buckets are numbered starting from 0, and every bucket stores approximately the same number of tuples. The values of histogram bounds are the bounds of the corresponding buckets. For example, the 0th value of the histogram bounds is 1, which means it is the minimum value of the tuples stored in bucket 0. The first value is 100, and this is the minimum value of the tuples stored in bucket 1, and so on. Next, the calculation of the selectivity using the example in this subsection will be shown. The query has a where clause, data is less than 240, and the value 240 is in the second bucket. In this case, the selectivity can be derived by applying linear interpolation. Thus, the selectivity of the column data in this query is calculated using the following equation. Selectivity equals 2 plus 240 minus HB at index 2 divided by HB index 3 minus HB index 2 divided by 100. So 2 plus 240 minus 200 divided by 300 minus 200, and we get 0.024. Thus, index CPU cost equals 0.024 times 10,000 times 0.005 plus 0.0025 equals 1.8. The table CPU cost is 0.024 times 10,000 times 0.01 equals 24, and the index IO cost is the ceiling of 0.024 times 30 times 4.0, which equals 4.0. And the table cost is defined by the following equation. The table IO cost equals max IO cost plus index correlation squared times the min IO cost minus the max IO cost. Max IO cost is the worst case of the IO cost, that is, the cost of randomly scanning all table pages. This cost is defined by the following equation. Max IO cost is the number of pages times the random page cost. In this case, according to 2, n page is 45, and thus max I/O cost is 45 times 4.0, which is 180. Min I/O cost is the best case of the I/O cost, that is, the cost of sequentially scanning the selected table pages. This cost is defined by the following equation. Min I/O cost is 1 times random page cost plus the ceiling of selectivity times number of page minus 1 times sequential page cost. In this case, min I/O cost equals 1 times 4.0 plus the ceiling of 0.024 times 45 minus 1 times 1 equals 5. Index correlation is described in detail below, and in this example, index correlation is 1.0. Thus, table I/O cost equals 180 plus 1 squared times 5 minus 180 equals 5. Finally, run cost equals 1.8 plus 2.4 plus 4.0 plus 5.0 equals 13.2. Index correlation. Index correlation is a statistical correlation between physical row ordering and logical ordering of the column values. This ranges from -1 to +1. To understand the relation between the index scan and the index correlation, a specific example is shown in the following. The table core has 5 columns. 2 columns are text type and 3 columns are integer type. The 3 integer columns store numbers from 1 to 12. Physically, table core is composed of 3 pages, and each page has 4 tuples. Each integer type column has an index with a name and is such, and name is such as index, call, ask, and so on. So describe table core, call ask, call desk, call rand, data. Select call ascending, call descending, call random. The index correlations of these columns are shown below. Select table name @name correlation from pgstats, where table name equals table core. When the following query is executed, Postgres reads only the first page because all target tuples are stored in the first page. Select star from table core where column ascending between 2 and 4. On the other hand, when the following query is executed, Postgres has to read all pages. Select star from table core where column rand between 2 and 4. This way, the index correlation is a statistical correlation that reflects the influence of random access caused by the twist between the index ordering and the physical tuple ordering in the table in estimating the index scan cost. Figure 3.8, index correlation. So we have correlation 1, correlation 0.12, column rand, column ascend. Total cost. Total cost equals 0.285 plus 13.2 equals 13.485. For confirmation, let's do an explain command. Explain select ID table or ID data from table where data is less than 240. And indeed, we see that the total cost and the start cost are shown. In line 4, we can find that the startup costs and the total costs are 0.29 and 13.49 respectively, and it is estimated that 240 rows tuples will be scanned. In line 5, an index condition, index cond data less than 240 of the index scan is shown. More precisely, this condition is called an access predicate. It expresses the start and stop conditions of the index scan. According to this post, the explain command in Postgres does not distinguish between the access predicate and index filter predicate. Therefore, if you analyze the output of explain, pay attention not only to the index conditions, but also to the estimated value of rows. Sequential page cost and random page cost. The default values of sequential page cost and random page cost are 1 and 4 respectively. This means that Postgres assumes the random scan is 4 times slower than the sequential scan. That is, obviously, the default value of the Postgres is based on using HDDs. On the other hand, in recent days, the default value of random page cost is too large because SSDs are mostly used. If the default value of random page cost is used despite using an SSD, the planner may select inefficient plans. Therefore, when using an SSD, it is better to change the value of random page cost to 1. This blog reported the problem when using the default value of random page cost. 3.2.3 Sort. The sort path is used for sorting operations, such as order by, the pre-processing of merge-join operations, and other functions. The cost of sorting is estimated using the cost-sort function. In the sorting operation, if all tuples have been sorted, in the sorting operation, if all tuples to be sorted can be stored in workmem, the quicksort algorithm is used. Otherwise, a temporary file is created and the file merge sort algorithm is used. The startup cost of the sort path is the cost of sorting the target tuples. Therefore, the cost is O of nsort times log base 2 of nsort, where nsort is the number of tuples to be sorted. The run cost of the sort path is the cost of reading the sorted tuples. Therefore, the cost is O of nsort. In this subsection, we explore how to estimate the sorting cost of the following query. Assume that this query will be sorted in workmem without using temporary files. Select ID data from table where data is less than 240. Order by ID. In this case, the startup cost is defined in the following equation. Startup cost equals C plus comparison cost times nsort times log base 2 of nsort, where C is the total cost of the last scan, that is, the total cost of the index scan. According to 15, it is 13.485. Nsort is 240. Comparison cost is defined as 2 times the CPU operator cost. Thus, startup cost equals 13.485 plus 2 times 0.0025 times 240 times log base 2 of 240 equals 22.973. The run cost is the cost to read sorted tuples in memory. Thus, run cost equals CPU operator cost times nsort equals 0.0025 times 240 equals 0.6. Finally, total cost equals 22.973 plus 0.6, which equals 23.573. And we can validate that with an explain. Oh, okay. Yes. Startup cost here, the total cost here. In line 4, we can find that the startup cost and total costs are 22.97 and 23.57 respectively. 3.3. Creating the plan tree of a single table query. As the processing of the planner is very complicated, this section describes the simplest process, that is, how a plan tree of a single table is created. More complex processing, namely how a plan tree of a multi-table query is created, is described in section 3.6. The planner in Postgres performs 3 steps as shown below. First, carry out pre-processing. 2, create the cheapest access path by estimating the costs of all possible access paths. And 3, create the plan tree from the cheapest path. An access path is a unit of processing for estimating the cost. For example, the sequential scan, index scan, sort, and various join operations have their corresponding paths. Access paths are used only inside the planner to create the plan tree. The most fundamental data structure of access paths is the paths structure, defined in relation.h, and it corresponds to the sequential scan. All other access paths are based on it. Details will be described in the following explanations. To process the above steps, the query internally creates a planner info structure and holds the query tree, the information about the relations contained in the query, the access paths, and so on. In this section, we'll explain how plan trees are created from query trees. How plan trees are created from query trees is described using specific examples. 3.3.1 Pre-processing. Before creating a plan tree, the planner carries out some pre-processing of the query tree stored in the planner info structure. Although processing involves many steps, we only discuss the main pre-processing for the single table query in this subsection. First, simplifying target lists, limit clauses, and so on. For example, 2 plus 2 is rewritten to 4 by the eval const expressions defined in expressions function defined in clauses.c. 2. Normalizing Boolean expressions. For example, not a is rewritten to a. Flattening and or expressions. And or in SQL standard are binary operators. However, in Postgres internals, they are n-ary operators, and the planner always assumes that all nested and or expressions are to be flattened. A specific example is shown. Consider a Boolean expression id equals 1 or id equals 2 or id equals 3. Figure 3.9 shows part of the query tree when using the binary operator. The operator simplified this tree by flattening using a ternary operator, non-flattened or flattened. (3.3.2) Getting the cheapest access path. To get the cheapest access path, the planner estimates the costs of all possible access paths and chooses the cheapest one. More specifically, the planner performs the following operations. First, create a rel opt info structure to store the access paths and corresponding costs. A rel opt info structure is created by the make1rel function and is stored in the simple rel array of the planner info structure. Refer to figure 3.10. In its initial state, the rel opt info holds the base restrict info and the index list if related indexes exist. The base restrict info stores the where clauses of the query. The indexed list and the index list stores the related indexes of the target table. Second, estimate the costs of all possible access paths and add access paths to the rel opt info structure. Details of this process are as follows. 2.1, a path is created, the cost of the sequential scan is estimated, and the estimated costs are written into the path. Then the path is added to the path list of the rel opt info structure. 2.2. If indexes related to the table target or to the target table exist, index access paths are created. All index scan costs are estimated and the estimated costs are written into the path. Then the index paths are added to the path list. 2.3. If the bitmap scan can be done, bitmap scans are created, all bitmap scan costs are estimated, and the estimated costs are written into the path. Then the bitmap scan costs are added to the path list. Third, get the cheapest access path in the path list of the rel opt info structure. And fourth, estimate limit, order by, and Arregis F DT costs if necessary. To understand how the planner performs clearly, two specific examples are shown below. 3.3 Example 1. First, we explore a simple single table query without indexes. This query contains both where and order by clauses. So select star from table 1 where ID is less than 300, order by data. So figures 3.10 and 11 depict how the planner performs this example. How to get the cheapest path of example 1. So it's planner info, query, parse, list, info, 2. So first, create a rel opt info structure and store it in the simple rel array of the planner info. Add a where clause to the base restrict info of the rel opt info. A where clause ID of ID less than 300 is added to the base restrict info by the distribute restrict info to rels function defined in inits plan.c. In addition, the index list of the rel opt is null because there are no related indexes of the target table. Three here. Add the path key for sorting to the sort path keys of the planner info by the standard QP callback function defined in planner.c. Path key is a data structure representing the sort ordering for the path. In this example, the column data is added to the sort path keys as a path key because this query contains an order by clause and its column is data. 4. Right here. Create a path structure and estimate the cost of the sequential scan using the cost sequential scan function and write the estimated costs into the path. Then add the path to the rel opt info by the add path function defined in pathnode.c. As mentioned before, the path structure contains both the startup and total costs, which are estimated by the cost sequential scan function, and so on. In this example, the planner only estimates the sequential scan cost because there are no indexes of the target table. Therefore, the cheapest access path is automatically determined. Figure 3.11. how to get the cheapest path of example 1. 5. Create a new rel opt info structure to process the order by procedure. Note that the new rel opt info does not have the base restrict info, that is, the information of the where clause. Create a sort path and add it to the new rel opt info. Then link the sequential scan path to the subpath of the sort path. The sort path structure is composed of two path structures, path and subpath. The path stores information about the sort operation itself, and the subpath stores the cheapest path. Note that the item parent of the sequential scan path holds the link to the old rel opt info, which stores the where clause in its base restrict info. Therefore, in the next stage, that is, creating a plan tree, the planner can create a sequential scan node that contains the where clause as the filter, even though the new rel opt info does not have the base restrict info. Based on the cheapest access path obtained here, a plan tree is generated. Example 2. Next, we explore another single table query with two indexes. This query contains a where clause. So we have index on data and primary key. Figures 3.12 to 3.14 depict how the planner performs this example. So first, create the rel opt info structure, add the where clause to the base restrict info, and add the indexes of the target table to the index list. In this example, a where clause ID is less than 240 is added to the base restrict info, and two indexes, table 2 p-key and table 2 data index, are added to the index list of the rel opt info. Then 3, create a path, estimate the cost of sequential scan, and add the path to the path list of the rel opt info. (3.13) Continued. 4. Create an index path, estimate the cost of index scan, and add index path to the path list of the rel opt info using the add path function. In this example, there are two indexes, table 2 p-key and table 2 data index. These indexes are processed in order. Table 2 p-key is processed first. An index path is created for table 2 p-key, and both the startup and total costs are estimated. In this example, table 2 p-key is the index related to the column ID, and the where clause contains the column ID. Therefore, the where clause is stored in the index clauses of the index path. Note that when adding access paths to the path list, the add path function adds paths in the sort order of the total cost. In this example, the total cost of this index scan is smaller than the sequential total cost. Thus, this index path is inserted before the sequential scan path. 5. Create another index path, estimate the cost of other index scans, and add the index path to the path list of the rel opt info. Next, an index path is created for table 2 data index. The costs are estimated, and this index path is added to the path list. In this example, there is no where clause related to the table2 data index. Thus, the index clauses are null. Note that the add path function does not always add the path. The details are omitted because of the complicated nature of this operation. 6. Create a new rel opt info structure. Add the cheapest path to the path list of the new rel opt info. In this example, the cheapest path is the index path using the index table2 p key. Thus, its path is added to the path list of the new rel opt info. 3.3.3 Creating a plan tree. At the last stage, a planner generates a plan tree from the cheapest path. The root of the plan tree is a plan statement structure defined in planNodes.h. While it contains 19 fields, here are 4 representative fields. Command type stores a type of operation, such as select, update, and insert. rtable stores range table entries. Relation OIDs stores OIDs of the related tables for this query. Plan tree stores a plan tree that is composed of plan nodes, where each node corresponds to a specific operation, such as sequential scan, sort, and index scan. As mentioned above, a plan tree is composed of various plan nodes. The plan node structure is the base node, and other nodes always contain it. For example, sequential scan node, which is for sequentially scanning, is composed of a plan node and an integer variable scan rel ID. A plan node contains 14 fields. The following are 7 representative fields. Startup cost and total cost are the estimated costs of the operation corresponding to this node. Rows is the number of rows to be scanned, which is estimated by the planner. Target list stores the target list items contained in the query tree. Qual is a list that stores qual conditions. Left tree and right tree are the nodes for adding the children nodes. In the following 2 plan trees, which will be generated from the cheapest paths shown in the examples in the previous subsection, are described. Example 1. The first example is the plan tree of the example in section 3.3.2.1. The cheapest path is shown in figure 3.11 is a tree composed of a sort path and a sequential scan path. The root path is the sort path, and the child path is the sequential scan path. Although detailed explanations are omitted, it will be easy to understand that the plan tree can be almost trivially generated from the cheapest path. In this example, a sort node is added to the plan tree of the plan statement structure, and a sequential scan node is added to the left tree of the sort node. Refer to figure 3.15a. Plan statement, command select, sort node, range table, relation OIDs. In the sort node, the left tree points to the sequential scan node. In the sequential scan node, the qual holds the where clause is less than 300. Example 2. The second example is the plan tree of the example in section 3.3.2.2. The cheapest path shown in 3.14 is the index scan path. Thus, the plan is composed of an index scan node structure alone. In this example, the where clause ID less than 240 is an access predicate. It is therefore stored in the index qual of the index scan node. 3.4. How the executor performs. In single table queries, the executor takes the plan nodes in an order from the end of the plan tree to the root and then invokes the functions that perform the processing of the corresponding nodes. Each plan node has functions that are meant for executing the respective operation, and they are located in the source backend executor directory. For example, the functions for executing the sequential scan are defined in node sequential scan.c. The functions for executing the index scan node are defined in node index scan.c. The functions for sorting sort node are defined in node sort.c, and so on. Of course, the best way to understand how the executor performs is to read the output of the explain command, because Postgres explain shows the plan tree almost as it is. It will be explained using example 1. Explain select star from table 1 where ID is less than 300. Order by data. Let's explore how the executor performs. Read the result of the explain command from the bottom line to the top line. Line 6. At first, the executor carries out a sequential scan operation using the functions defined in node sequential scan.c. Next, the executor sorts the results of the sequential scan using the functions in node sort.c. Temporary files. Although the executor uses workmem and temp buffers, which are allocated in memory for query processing, it uses temporary files if processing cannot be performed within only the memory. Using the analyze option, the explain command actually executes the query and displays the true row counts, true runtime, and actual memory usage. Explain, analyze, select ID data from table 25M, order by ID. It's the query plan. In line 6, the explain command shows the executor has used a temporary file whose size is 10,000 kilobytes. Temporary files are created in the base pgtemp subdirectory temporarily, and the naming method is shown below. So pg is equal temp plus the PID of the Postgres process which creates the file, and dot sequential number from 0. For example, the temporary file pg is equal temp 8903.5 is the 6th temporary file that is created by the Postgres process whose PID is 8903. Join operations. Postgres supports 3 join operations: nested loop join, merge join, and hash join. The nested loop join and merge join in Postgres have several variations. In the following, we will assume the reader is familiar with the basic behaviors of these 3 joins. However, as there is not much explanation on the hybrid hash join with skew supported by Postgres, it will be explained in more detail here. Note that the 3 join methods supported by Postgres can perform all join operations, not only inner join, but also left, right, outer join, full outer join, and so on. However, for simplification, we focus on the natural inner join in this chapter. 3.5.1 Nested loop join. The nested loop join is the most fundamental join operation, and it can be used in any join conditions. Postgres supports the nested loop join and 5 variations of it. First variation, or 3.5.1.1, nested loop join. The nested loop join does not need any startup operation, thus startup cost is 0. The run cost of the nested loop join is proportional to the product of the size of the outer and the inner tables. That is, the run cost is O of n outer times n inner, where n outer and n inner are the numbers of tuples of the outer table and inner table, respectively. More precisely, it is defined by the following equation. Run cost equals CPU operator cost plus CPU tuple cost times n outer times n inner plus c inner times n outer plus c outer, where C outer and C inner are the scanning costs of the outer table and inner table, respectively. Figure 3.6, nested loop join. Outer, inner. The cost of the nested loop join is always estimated, but this join operation is rarely used because more efficient variations that are described in the following are usually used. 3.5.1.2 Materialized nested loop join. The nested loop join described above has to scan all the tuples of the inner table whenever each tuple of the outer table is read. As scanning the entire inner table for each outer table tuple is a costly process, Postgres supports the materialized nested loop join to reduce the total scanning cost of the inner table. Before running a nested loop join, the executor writes the inner table tuples to workmem or a temporary file by scanning the inner table once using the temporary tuple storage module described below. It has a potential to process the inner table tuples more efficiently than using the buffer manager, especially if at least all the tuples are written to workmem. Figure 3.7 illustrates how the materialized nested loop join performs. Scanning materialized tuples is internally called rescan. Outer, inner, materialize, scan, outer, rescan. Temporary tuple storage. Postgres internally provides a temporary tuple storage module for materializing tables, creating batches in hybrid hash join, and so on. This module is composed of the functions defined in tuplestore.c, and then they store and read a sequence of tuples to and from work memory or temporary files. Whether the workmem or the temporary files are used depends on the total size of the tuples to be stored. We explore how the executor processes the plan tree of the materialized nested loop join and how the cost is estimated using the specific example shown below. Explain select star from table A as A, table B as B, where A.id equals B.id. At first, the operation of the executor is shown. The executor processes the displayed plan nodes as followed. Line 7. The executor materializes the inner table table B by sequentially scanning. Line 4. the executor carries out the nested loop join operation. The outer table, table A, and the inner one is the materialized table B. In what follows, the cost of materialize, line 7, and nested loop on line 4 are estimated. Assume that the materialized inner tuples are stored in workmem. Materialize. There is no cost to startup, thus startup cost is 0. The run cost is defined by the following equation. Run cost is 2 times the CPU operator cost times the number of n inner. Thus, run cost is 2 times 0.0025 times 5,000, which equals 25. In addition, total cost equals the startup cost plus the total cost of sequential scan plus run cost. So total cost is 0 plus 73 plus 25, which equals 98. Materialized nested loop. There's no cost to startup, thus startup cost is 0. Before estimating the run cost, we consider the rescan cost. This cost is defined by the following equation. Rescan cost equals the CPU operator cost times n inner. In this case, rescan cost equals 0.0025 times 5,000, or 12.5. The run cost is defined by the following equation. Run cost equals CPU operator cost plus CPU tuple cost times n inner times n outer plus rescan cost times n outer minus 1 plus C total outer sequential scan plus C total materialize, where C total outer scan is the total scan cost of the outer table and C total materialize is the total cost of the materialized. Therefore, run cost equals 0.0025 plus 0.01 times 5,000 times 10,000 plus 12.5 times 1,000 minus 1 plus 145 plus 98 for a sum of 750,230.5. 3.5.1.3 Indexed nested loop join. If there is an index of the inner table, and this index can look up the tuples satisfying the join condition for matching each tuple of the outer table, the planner considers using this index for directly searching the inner table tuples instead of sequentially scanning. This variation is called indexed nested loop join. Refer to Figure 3.18. Despite the fact that it referred to the indexed nested loop join, this algorithm can process on the basis of a single loop of the outer table. Therefore, it can perform the join operation efficiently. A specific example of the indexed loop join is shown below. Explain select star from table C as C, table B as B, where CID equals BID. On line 6, the cost of accessing a tuple of the inner table is displayed. This is the cost of looking up the inner table if the tuple satisfies the index condition, ID equals BID, shown on line 7. In the index condition, ID equals BID in line 7, BID is the value of the outer table's attribute using the join condition. Whenever a tuple of the outer table is retrieved by sequential scanning, the index scan path in line 6 looks up the inner tables to be joined. In other words, whenever the outer table's value is passed as a parameter, this index scan path looks up the inner tuples that satisfy the join condition. Such an index path is called a parameterized index path. Details are described in the README. The startup cost of this nested loop join is equal to the cost of the index scan in line 6. Thus, startup cost equals 0.285. The total cost of the indexed nested loop join is defined by the following equation. Total cost equals CPU tuple cost plus C of total inner parameterized times N outer plus C run outer sequential scan, where C total inner parameterized is the total cost of the parameterized inner index scan. In this case, total cost equals 0.01 plus 0.3625 times 5,000 plus 73 equals 1935.5. And the run cost is 19.35.5 minus 0.285, which is 1935.215. As shown above, the total cost of the indexed nest loop is O of N outer. 3.5.1.4 Other variations. If there is an index of the outer table and its attributes are involved in the join condition, it can be used for the index scanning instead of the sequential scan of the outer table. In particular, if there is an index whose attribute can be an access predicate in the where clause, the search range of the outer table is narrowed. Therefore, the cost of the nested loop join may be drastically reduced. Postgres supports 3 variations of the nested loop join with an outer index scan. Refer to Figure 3.19. The results of these joins explains are shown here. A. Nested loop join with outer index scan. Enable hash. 2. Materialized nested loop with outer index scan. 3. Indexed nested loop join with outer index scan. 3.5.2 Merge join. Unlike the nested loop join, merge join can be only used in natural joins and equijoins. The cost of the merge join is estimated by the initial cost merge join and final cost merge join functions. As the exact cost estimation is complicated, it is omitted and only the runtime order of the merge join algorithm is shown. The startup cost of the merge join is the sum of sorting costs of both inner and outer tables. Thus, the startup cost is O of N outer log base 2 of N outer plus N inner log base 2 of N inner, where N outer and N inner are the number of tuples of the outer and inner tables respectively. The run cost is O of N outer plus N inner. Similar to the nested loop join, the merge join in Postgres has 4 variations. 3.5.2.1 Merge join. Figure 320 shows a conceptual illustration of a merge join. If all tuples can be stored in memory, the sorting operations will be able to be carried out in the memory itself. Otherwise, temporary files are used. A specific example of the explain commands result of the merge join is shown below. Explain select star from table A as A, B as B, where A ID equals B ID, and B ID is less than 1,000. Line 9. The executor sorts the inner table, table B, using sequential scanning. Line 6. The executor sorts the outer table, table A, using sequential scanning. Line 4. The executor carries out a merge join operation. The outer table is the sorted table A, and the inner one is the sorted table B. 3.5.2.2 Materialized merge join. Same as in the nested loop join, the merge join also supports the materialized merge join to materialize the inner table to make the inner table scan more efficient. Materialized merge join. An example of the result of the materialized merge join is shown. It is easy to find the difference from the merge join result above in line 9. Materialize. Line 10. The executor sorts the inner table, table B, using sequential scanning. Line 9. The executor materializes the result of the sorted table B. Line 6. The executor sorts the outer table, table A, using sequential scanning. And line 4. The executor carries out a merge join operation. The outer table is sorted table A, and the inner one is the materialized sorted table B. 3.5.2.3 Other variations. Similar to the nested loop join, the merge join in Postgres has variations based on which the index scanning of the outer table can be carried out. The 3 variations of the merge join with an outer index scan. (3.5.3) Hash join. Similar to the merge join, the hash join can only be used in natural joins and equijoins. The hash join in Postgres behaves differently depending on the sizes of the tables. If the target table is small enough, more precisely, the size of the inner table is 25% or less of work mem, it will be a simple 2-phase in-memory hash join. Otherwise, the hybrid hash join is used with the skew model. In this subsection, the execution of both hash joins in Postgres is defined. Discussion of the cost estimation has been omitted because it's complicated. Roughly speaking, the startup and run costs are O of n outer plus n inner, if assuming there is no conflict when searching and inserting into a hash table. 3.5.3.1 In-memory hash join. In this subsection, the in-memory hash join is described. This in-memory hash join is processed on workmem, and the hash table area is called a batch in Postgres. A batch has hash slots, internally called buckets, and the number of buckets is determined by the exec choose hash table size function defined in node hash c. The number of buckets is always 2 to n, where n is an integer. The in-memory hash join has 2 phases, the build and the probe phases. In the build phase, all tuples of the inner table are inserted into a batch. In the probe phase, each tuple of the outer table is compared with the inner tuples in the batch and joined if the join condition is satisfied. A specific example is shown to clearly understand this operation. Assume the query shown below is executed using a hash join. Select star from table outer as outer, table inner as inner, where inner.adder1 equals outer.adder2. In the following, the operation of a hash join is shown. The build phase in the in-memory hash join. 1. Create a batch on workmem. In this example, the batch has 8 buckets. That is, the number of buckets is 2 to the 3rd power. 2. Insert the first tuple of the inner table into the corresponding bucket of the batch. The details are given below. Calculate the hash key of the first tuple's attribute, which is involved in that join condition. In this example, the hash key of the attribute adder1 of the first tuple is calculated using the built-in hash function, because the where clause is inner.adder1 equals outer.adder2. Then, insert the first tuple into the corresponding bucket. Assume that the hash key of the first tuple is OX000.001 by binary notation. That is, the last 3 bits are 001. In this case, this tuple is inserted into the bucket which has the key 001. In this document, such insertion operation to build a batch is represented by this operator. Inserting then 3, insert the remaining tuples of the inner table. Figure 3.4, the probe phase in the in-memory hash join. 4. Probe the first tuple of the outer table. Calculate the hash key of the first tuple's attribute, which is involved in the join condition of the outer table. And in this example, assume that the hash key of the first tuple's attribute, adder2, is the last 3 bits are 100. 2. Compare the first tuple of the outer table with the inner tuples in the batch and join tuples if the join condition is satisfied. Because the last 3 bits of the hash key of the first tuple are 100, the executor retrieves the tuples belonging to the bucket whose key is 100 and compares both values of the respective attributes of the tables specified by the join condition, defined by the where clause. If the join condition is satisfied, the first tuple of the outer table and the corresponding tuple of the inner table will be joined. Otherwise, the executor does not do anything. In this example, the bucket whose key is 100 has tuple C. If the adder1 of tuple C is equal to the adder2 of the first tuple, tuple W, then tuple C and tuple W will be joined and saved to memory or a temporary file. In this document, such an operation to probe a batch is represented by this operator. 5. Probe the remaining tuples of the outer table. 3.5.3.2 Hybrid hash join with skew. When the tuples of the inner table cannot be stored into one batch in workmem, Postgres uses the hybrid hash join with the skew algorithm, which is a variation based on the hybrid hash join. At first, the basic concept of the hybrid hash join is described. In the first build and the probe phases, Postgres prepares multiple batches. The number of batches is the same as the number of buckets, determined by the exec choose hash table size function. It is always 2 to the m, where m is an integer. At this stage, only one batch is allocated in workmem, and the other batches are created as temporary files. And the tuples belonging to these batches are written to the corresponding files and saved using temporary tuple storage feature. Figure 3.25 illustrates how tuples are stored in 4 to the 2 batches. In this case, which batch stores each tuple is determined by the first 2 bits of the last 5 bits of the tuple's hash key. Because the sizes of the buckets and batches are 2 to the 3rd and 2 to the 2nd respectively, batch 0 stores the tuples whose last 5 bits of the hash key are between 00000 and 00111. Batch 1 stores the tuples whose last 5 bits of the hash key are between 01, 000, and 01, 111, and so on. In the hybrid hash join, the build and probe phases are performed the same number of times as the number of batches, because the inner and outer tables are stored in the same number of batches. In the first round of the build and probe phases, not only is every batch created, but also the first batches of both the inner and outer tables are processed. On the other hand, the processing of the second and subsequent rounds needs writing and reloading to and from the temporary files, so these are costly processes. Therefore, Postgres also prepares a special batch called SKU to process many tuples more efficiently in the first round. The SKU batch stores the inner table tuples that will be joined with the outer table tuples whose most common values of the attribute involved in the join condition are relatively large. However, this explanation is not easy to understand, and it will be explained using a specific example. Assume that there are two tables, customers and purchase history. The customers table is composed of two attributes, a name and his or her address. The purchase history table is composed of two attributes, the customer name and purchased item. The customers table has 10,000 rows, and the purchase history table has 1 million rows. The top 10% customers have purchased 70% of all items. Under these assumptions, let us consider how the hybrid hash join with SKU performs in the first round when the query shown below is executed. Select star from customers as C, purchase history as H, where c.name equals h.customer_name. If the customers table is inner and the purchase history is outer, the top 10 customers are scored in the SKU batch using the most common values of the purchase history table. Note that the outer table's most common values are referenced to insert the inner table tuples into the SKU batch. In the probe phase of the first round, 70% of the tuples of the outer table, purchase history, will be joined with the tuples stored in the SKU batch. This way, the more non-uniform of the outer table distribution, it can be processed many tuples of the outer table in the first round. The more non-uniform of the outer table distribution, it can be processed many tuples of the outer table in the first round. In the following, the working of the hybrid hash join with SKU is shown. The build phase. First, create a batch and a SKU batch on workmem. 2. Create temporary batch files for storing the inner table tuples. In this example, 3 batch files are created because the inner table will be divided by 4 batches. 3. Perform the build operation of the first tuple of the inner table, which involves if the first tuple should be inserted into the SKU batch, do it. Otherwise, proceed to 2. In the example above, if the first tuple is one of the top 10% customers, it is inserted into the SKU batch. Then, calculate the hash key of the first tuple and then insert the corresponding batch. 4. Perform the build operation for the remaining tuples of the inner table. The probe phase. 5. Create the temporary batch files for storing the outer table tuples. 6. If the most common value of the first tuple is large, perform a probe operation with a SKU batch. Otherwise, proceed to 7. In the example explained above, if the first tuple is the purchase data of the top 10% customers, it is compared with the tuples in the SKU batch. 7. Perform the probe operation of the first tuple. Depending on the hash key value of the first tuple, the following process is performed. If the first tuple belongs to batch 0, perform the probe operation. Otherwise, insert it into the corresponding batch. 8. Perform the probe operation for the remaining tuples of the outer table. Note that, in the example, 70% of the tuples of the outer table have been processed by the skew in the first round. 3.28. The build and probe phases in the second round. 9. Remove the skew batch and clear batch 0 to prepare the second round. 10. Perform the build operation from the batch file batch1 in. 11. Perform the probe operation for tuples which are stored in batch file batch1 out. And the third and last rounds. 12. Perform the build and probe operation using batch files batch2 in and batch2 out. And 13. Perform the build and probe operations using the batch files batch3 in and batch3 out. 3.5.4. Join access paths and join nodes. 3.5.4.1. Join access paths. An access path of the nested loop join is the join path structure, and other join access paths, merge path, and hash path are based on it. All join access paths are illustrated in the following without explanation. Nested loop join, materialized nested loop join, index loop join, merge join, and hash join. (3.5.4.2) Join nodes. This subsection shows the 3 join nodes without explanation: nested loop node, merge join node, and hash join node. They're based on join node. 3.6 Creating the plan tree of multiple table query. In this section, the process of creating a plan tree of a multiple table query is explained. 3.6.1 Pre-processing. The subquery planner function described in Planner C invokes pre-processing. The pre-processing for single table queries has already been described above. In this subsection, the pre-processing for multiple table query will be described. However, although there are many, only some parts are described. First, planning and converting the common table expressions. If there are with lists, the planner processes each with query by the ss process common table expressions function, pulling subqueries up. If the from clause has a subquery and it does not have group by, having, order by, limit, and distinct clauses, and also it does not use intersect or except, the planner converts to a join form by the pull-up subqueries function. For example, the query shown below contains a subquery in the from clause. For example, the query shown below, which contains a subquery in the from clause, can be converted to a natural join query. Needless to say, this conversion is done in the query tree. (3) Transforming an outer join to an inner join. The query performs an outer join query to an inner join, transforms an outer join query to an inner join query if possible. 3.6.2 Getting the cheapest path. To get the optimal plan tree, the planner has to consider the combinations of all the indexes and join methods possible. This is a very expensive process, and it will be infeasible if the number of tables exceeds a certain level because of a combinational explosion. Fortunately, if the number of tables is smaller than around 12, the planner can get the optimal plan by applying dynamic programming. Otherwise, the planner uses the genetic algorithm. Genetic query optimizer. When a query joining many tables is executed, a huge amount of time will be needed to optimize the query plan. To deal with this situation, Postgres implements an interesting feature, the genetic query optimizer. This kind of approximate algorithm to determine a reasonable plan within a reasonable time. Hence, the query optimization stage, if the number of joining tables is higher than the threshold specified by the parameter GEQO threshold, the default is 12, Postgres generates a query plan using the genetic algorithm. Determination of the optimal plan tree by dynamic programming can be explained by the following steps. Level 1. Get the cheapest path of each table. The cheapest path is stored by the respective rel opt info. Level 2. Get the cheapest path for each combination that selects 2 from all the tables. For example, if there are 2 tables, A and B, get the cheapest join path of the tables A and B, and this is the final answer. In the following, the rel opt info of the 2 tables is represented as by AB. If there are 3 tables, get the cheapest path for each of AB, AC, and BC. Level 3 and higher. The same processing is continued until the level that equals the number of tables is reached. This way, the cheapest paths of the partial problems are obtained at each level and are used to get the upper levels calculation. This makes it possible to calculate the cheapest plan tree efficiently. How to get the cheapest access paths using dynamic programming. In the following, the process of how the planner gets the cheapest plan of the following is described. Processing in Level 1. In Level 1, the planner creates a rel opt info structure and estimates the cheapest costs of each relation in the query. There, rel opt info structures are added to the simple rel array of the planner info of this query. The rel info of table A has 3 access paths, which are added to the path list of the rel opt info. They are linked to 3 cheapest costs paths, that is, the cheapest startup cost path, the cheapest total cost path, and the cheapest parameterized cost path. As the cheapest startup and total cost paths are obvious, the cost of the cheapest parameterized index scan path will be described. As described above, the planner considers the use of the parameterized path for the index nested loop join, and rarely the index merge join with an outer index scan. The cheapest parameterized cost is the cheapest cost of the estimated parameterized paths. The rel opt info of table B only has a sequential scan access path because table B does not have a related index. 3.6.2.2 Processing in Level 2. In Level 2, a rel opt info structure is created and added to the join rel list of the query of the planner info. Then the costs of all possible join paths are estimated, and the best access path, whose total cost is the cheapest, is selected. The rel opt info stores the best access path as the cheapest total cost path. Table 3.1 shows all combinations of join access paths in this example. The query of this example is an equal join type. Therefore, all the three join methods are estimated. For convenience, some notations of access paths are introduced. Sequential scan path of table means the sequential scan path of a table. Materialized sequential scan path of a table means the materialized sequential scan path of a table. Index scan path of a table for an attribute means the index scan path by the attribute of the A table of the table. Parameterized index scan path of a table, attribute 1, attribute 2, means the parameterized index scan path by the attribute 1 of the table, and it is parameterized by attribute 2 of the outer table. For example, in the nested loop join, 7 join paths are estimated. The first one indicates that the outer and inner paths are sequential paths of table A and table B, respectively. The second indicates that the outer path is the sequential scan path of table A, and the inner path is the materialized sequential scan of path of table B, and so on. The planner finally selects the cheapest access path from the estimated join paths, and the cheapest path is added to the path list of the rel opt info, table A, table B. In this example, as shown in the result of explained below, the planner selects the hash join whose inner and outer tables are table B and table C. .6.3 Getting the cheapest path of a triple table query. Obtaining the cheapest path of a query involving 3 tables is given below. So we have table A, B, and C. Then we join them all. Level 1. The planner estimates the cheapest paths of all tables and stores this information in the corresponding rel opt infos, table A, table B, and table C. Level 2. The planner picks all the combinations of the pairs of the 3 tables and estimates the cheapest path of each combination. The planner then stores this information in the corresponding rel opt infos, table A, table B, table B, table C, and table A, table C. Level 3. The planner finally gets the cheapest path using the already obtained rel opt infos. More precisely, the planner considers 3 combinations of rel opt infos. Table A to table B, table C, table B to table A, table C, and table C to table A, table B, because table A, table B, table C is shown below. The min of these. The planner then estimates the costs of all possible join paths in them. In the rel opt info, table C to table A, table B, the planner estimates all the combinations of table C and the cheapest path of table A, table B, which is the hash join whose inner and outer tables are table A and table B respectively in this example. The estimated join paths will contain 3 kinds of join paths and their variations, such as shown in the previous subsection. That is, the nested loop join and its variations, the merge join and its variations, and the hash join. The planner processes the rel opt infos, table A, table B, table C, and table B, table A, table C, in the same way, and finally selects the cheapest access path from all the estimated paths. Then let's do an explain on it. The outermost join is the index nested loop on line 5. The inner parameterized sequential scan shown in line 13, and the outer relation is the result of the hash join whose inner and outer tables are table B and table A respectively. Therefore, the executor at first executes the hash join of table A and table B, then executes the index nested loop join. Wowza. Chapter 4, Foreign Data Wrappers in Parallel Query. Give me just a second. Gotta stand up. Okay. Chapter 4, Foreign Data Wrappers and Parallel Query. This chapter will describe two technically interesting and practical features: foreign data wrappers and parallel query. But parallel query is under construction. 4.1. In 2003, a specification to access remote data called SQL Management of External Data, SQL MED, was added to the SQL standard. This feature has been developed by Postgres to realize a portion of SQL MED since version 9.1. In SQL MED, a table on a remote server is called a foreign table. Postgres's foreign data wrappers, FDW, use SQL MED to manage foreign tables, which are similar to local tables. Here's a basic concept of foreign data wrappers. So you have a local server, and then you have these remote servers. After installing the necessary extension and making the appropriate settings, you can access the foreign tables on the remote servers. For example, suppose there are two remote servers, namely Postgres and MySQL, which have foreign PG table and foreign MyTable respectively. In this example, you can access the foreign tables from the local server by issuing the select queries as shown. Select count from foreign PG table and select count from foreign MyTable. Moreover, you can execute the join operation with the foreign tables stored in different servers, which are similar to local tables. So select count from foreign PG table as PG and foreign MyTable as M, where p.id equals m.id. Many foreign data wrapper extensions have been developed and listed in the Postgres wiki. However, almost all extensions are not properly maintained except for Postgres FDW, which is officially developed and maintained by the Postgres Global Development Group as an extension to access a remote Postgres server. Postgres's FDW is described in detail in the following sections. Citus. Citus is an open source PostgreSQL or Postgres extension produced by Citus Data to create a distributed server cluster for query parallelization. It is one of the most mechanically complex and commercially successful extensions of Postgres, and is also a type of FDW. 4.1.1 Overview. To use the FDW feature, you need to install the appropriate extension and execute setup commands such as create foreign table, create server, and create user mapping. After providing the appropriate setting, the functions defined in the extension are evoked during query processing to access the foreign tables. Figure 4.2. How foreign data wrappers perform. A local server, and you have a remote server, parser, analyzer, rewriter, planner, executor. 1. The analyzer creates the query tree of the input SQL. The planner, or executor, connects to the remote server. The use remote estimate option. If the use remote estimate option is on, the default is off, the planner executes explain commands for estimating the cost of each plan path. The planner creates the plain text SQL statement from the plan tree, which is internally called deparsing? Don't know. The executor sends the plain text SQL statement to the remote server and retrieves the result. The executor then processes the received data if necessary. For example, if the multi-table data is executed, the executor performs the join processing of the received data and other tables. The details of each processing are described in the following sections. 4.1.1.1 Creating a query tree. The analyzer creates the query tree of the input SQL using the definitions of the foreign tables, which are stored in the pgcatalog.pg class and pgcatalog.pg foreign table catalogs using the create foreign table or import foreign schema command. 4.1.1.2 Connecting to the remote server. To connect to the remote server, the planner, or executor, uses the specific library to connect to the remote database server. For example, to connect to the remote database, to the remote Postgres server, Postgres_FDW uses the libpq. To connect to the MySQL server, MySQL_FDW, which is developed by Enterprise DB, uses the libMySQL client. The connection parameters, such as username, server's IP address, and port number, are stored in the pgcatalog.pg user mapping and pgcatalog.pg foreign server catalogs using the create user mapping and create server commands. 4.1.1.3 Creating a plan tree using explain commands. Optional. Postgres's foreign data wrapper supports the feature to obtain statistics of the foreign tables to estimate the plan tree of a query, which are used by some foreign data wrapper extensions, such as Postgres foreign data wrapper, MySQL foreign data wrapper, TDS foreign data wrapper, and JDBC2 foreign data wrapper. If the use remote estimate option is set to on using the alter server command, the planner queries the cost of plans to the remote server by executing the explain command. Otherwise, the embedded constant values are used by default. Alter server remote server name options. Use remote estimate on. Although some extensions use the values of the explain command, only Postgres foreign data wrappers can reflect the results of the explain commands because the Postgres's explain command returns both the startup and total costs. The results of the explain command could not be used by the other database management systems, foreign data wrapper extensions for planning. For example, MySQL's explain command only returns the estimated number of rows. However, Postgres's planner needs more information to estimate the cost. 4.1.1.4 Deep parsing. To generate the plan tree, the planner creates the plain text SQL statement from the plan tree's scan paths of the foreign tables. For example, figure 4.3 shows the plan tree of the following select statement. Select star from table A, where table A as A, where A.id is less than 10. Figure 4.3 shows that the foreign scan node, which is linked from the plan tree of the plan statement, stores a plain select text. Here, Postgres's foreign data wrapper recreates a plain select text from the query tree that has been created by parsing and analyzing, which is called deparsing in Postgres. The use of MySQL's foreign data wrappers recreates a select text for MySQL for the query tree. The use of Redis foreign data wrappers, or RW Redis foreign data wrappers, creates a select command. 4.1.1.5 Sending SQL statements and receiving result. After deparsing, the executor sends the deparsed SQL statements to the remote server and receives the result. The method for sending the SQL statements to the remote server depends on the developer of each extension. For example, MySQL foreign data wrapper sends the SQL statements without using a transaction. The typical sequence of SQL statements to execute a select query in MySQL foreign data wrapper is shown below. Set SQL mode ANSI quotes, and sends it, and then send the data. Set the SQL mode to ANSI quotes, send a select statement to the remote server, receive the result from the remote server. Here, MySQL foreign data wrapper converts the result to readable data by Postgres. All foreign data wrapper extensions implemented the feature that converts the result to Postgres readable data. The actual log of the remote server can be found here, and the statements received by the remote server are shown. In Postgres foreign data wrapper, the sequence of SQL statements is complicated. The typical sequence of SQL statements is to execute a select query in the Postgres foreign data. The typical sequence of SQL statements to execute a select query in Postgres foreign data wrapper is shown below. Start the remote transaction. The default remote transaction isolation level is repeatable read. If the isolation level of the local transaction is set to serializable, the remote transaction is also set to serializable. 5.2 to 5.4. Declare a cursor. The SQL statement is basically executed as a cursor. 5.5. Execute fetch commands to obtain the result. By default, 100 rows are fetched by the fetch command. 5.6. Receive the result from the remote server. 5.7. Close the cursor. And 5.8. Commit the transaction. The default remote transaction isolation level in Postgres foreign data wrapper. The explanation for why the default remote transaction isolation level is repeatable read is provided in the official document. The remote transaction uses the serializable isolation level when the local transaction has the serializable isolation level. Otherwise, it uses the repeatable read isolation level. This choice ensures that a query performs multiple table scans on the remote server. That if a query performs multiple table scans on the remote server, it will get a snapshot consistent results for all the scans. A consequence is that successful queries within a single transaction will see the same data from the remote server, even if concurrent updates are occurring on the remote server due to other activities. 4.1.2 How the Postgres Foreign Data Wrapper extension performs. Postgres Foreign Data Wrapper extension is a special module that is officially maintained by the Postgres Global Development Group, and its source code is included in the Postgres source code tree. Postgres Foreign Data Wrapper is gradually improved. Table 4.1 presents the release notes related to Postgres Foreign Data Wrapper from the official document. 9.3 The Foreign Data Wrapper module is released. 9.6 Consider performing sorts on the remote server. Consider performing joins on the remote server. When feasible, perform update or delete entirely on the remote server. Allow the fetch size to be set as a server or table option. 10. Push aggregate functions to the remote server when possible. Given that the previous section describes how Postgres Foreign Data Wrapper processes a single table query, the following subsection shows how Postgres Foreign Data Wrapper processes a multi-table query, sort operation, and aggregate functions. This subsection focuses on the select statement. However, Postgres Foreign Data Wrapper can also process other DML, insert, update, and delete statements, as shown below. Postgres's Foreign Data Wrapper does not detect deadlock. Postgres Foreign Data Wrapper and the Foreign Data Wrapper feature do not support the distributed lock manager and the distributed deadlock detection feature. Therefore, a deadlock can be easily generated. For example, if client A updates a local table local and a foreign table remote, and client B updates table remote and table local, these two transactions are in deadlock, but could not be detected by Postgres. Therefore, these transactions could not be committed. 4.1.2.1 Second. To execute a multi-table query, Postgres Foreign Data Wrapper fetches each foreign table using a single table select statement and then joins them on the local server. In version 9.5 or earlier, even if the foreign tables are stored in the same remote server, Postgres Foreign Data Wrapper fetches them individually and joins them. In version 9.6 or later, Postgres Foreign Data Wrapper has been improved and can execute the remote join operation on the remote server when the foreign tables are on the same server and use the use remote estimate option is on. The execution details are described as follows. Version 9.5 or earlier. Let's explore how Postgres processes the following query that joins two foreign tables, Table A and Table B. The result of the explain query is shown below. Foreign scan. The result shows the executor selects the merge join and is processed as the following steps. Line 8. The executor fetches the table A using the foreign table scan. Line 6. the executor sorts the fetch rows of table A on the local server. Line 11. The executor fetches the table B using the foreign table scan. And on line 9, the executor sorts the fetch rows of table B on the local server. Then line 4, the executor carries out a merge join operation on the local server. The following describes how the executor fetches the rows. 5.1. Start the remote transaction. Declare cursor C1, the select statement of which is shown below. Execute fetch commands to obtain the result of cursor 1. Declare cursor 2, whose select statement is shown below, to table B. Note that the where clause of the original double table query is table A.id equals table B.id, and table ID and table A ID is less than 200. Therefore, a where clause, table B ID is less than 200, can be logically added to the select statement as shown previously. However, Postgres foreign data wrapper cannot perform this inference. Therefore, the executor has to execute the select statement that does not contain any where clauses and has to fetch all rows of the foreign table B. This process is inefficient because unnecessary rows must be read from the remote server via the network. Furthermore, the received results must be sorted to execute the merge join. 5.5. Execute fetch commands to obtain the result of cursor 2. 5.6. Close cursor 1. 5.7. Close cursor 2. 5.8. Commit the transaction. The actual log of the remote server can be found here. After receiving the rows, the executor sorts both received rows of table A and table B, and then executes a merge join operation with the sorted rows. Version 9.6 or later. If the use remote estimation option is on, the default is off. Postgres foreign data wrapper sends several explain commands to obtain the costs of all plans related to the foreign tables. To send the explain commands, Postgres foreign data wrapper sends both the explain command of each single table query and the explain commands of the select statements to execute remote join operations. In this example, the following 7 explain commands are sent to the remote server to obtain the estimated cost of each select statement. The planner then selects the cheapest plan. Let us execute the explain command on the local server to observe what plan is selected by the planner. So explain select star from table A as A, table B as B, where A ID equals B ID and A ID equals 200. Foreign scan. The result shows the planner selects the inner join query that is processed on the remote server, which is very efficient. The following describes how Postgres foreign data wrapper is performed. So we start the remote transaction. We execute explain commands for estimating the cost of each plan path. In this example, 7 explain commands are executed. Then the planner selects the cheapest cost of the select queries using the result of the executed explain commands. Then we declare cursor 1, whose select statement is shown below. Receive the result from the remote server, close the cursor 1, and commit the transaction. Note that if the use remote estimate option is off by default, a remote join query is rarely selected because the costs are estimated using a very large embedded value. 4.1.2.2 Sort operations. In version 9.5 or earlier, the sort operation, such as order by, is processed on the local server, i.e., the local server fetches all the target rows from the remote server prior to the sort operation. Let us explore how a simple query that includes an order by clause is processed using the explain command. So explain select star from table A where a.id is less than 200, order by AID. Line 6. The executor sends the following query to the remote server and then fetches the query result. Select ID data from public table ID where ID is less than 200. And line 4. The executor sorts the fetched rows of table A on the local server. In version 9.6 or later, Postgres foreign data wrapper can execute the select statements with an order by clause on the remote server if possible. The executor sends the following query that has an order by clause to the remote server and then fetches the query result, which is already sorted. Nice. The workload of the local server has been reduced by this improvement. 4.1.2.3 Aggregate Functions. In version 9.6 or earlier, similar to the sort operation mentioned in the previous section, the aggregate functions such as average and count are processed on the local server as the following steps. Explain select average data from table A where A ID is less than 200. Aggregate is performed on local. The executor sends the following query to the remote server and then fetches the query result. Select ID data from public table where ID is less than public table A where ID is less than 200. Then on line 4, the executor calculates the average of the fetched rows of table A on the local server. This process is costly because sending a large number of rows consumes heavy network traffic and takes a long time. In version 10 or later, Postgres foreign data wrapper executes the select statement with the aggregate function on the remote server if possible. Line 4. Executor sends the following query that contains an average function to the remote server and then fetches the query result. This process is obviously efficient because the remote server calculates the average and only sends one row as the result. Push down. Similar to the given example, the push down is an operation. The push down is an operation where the local server allowed the remote server to process some operations, such as procedures. Parallel query under construction. Chapter 5. We're going to come back to reading this another time. Thanks for hanging out. See ya.